Hello friends, so today we are going to discuss few questions, total 4 questions, and these 4 questions will be with respect to the moment of inertia as well as some stability concept rather. So in this case we can start with the first question, and the first question gives us that we have consider a square of side length A, remove the central square which occupies 1/9 of the area. Next, from each of the remaining 8 smaller squares, remove their respective central squares and continue this process infinitely. Let the resulting fractal-like object have mass m. The axis of rotation passes through the center of the square perpendicular to its plane. Okay, so this is the basic question. And in this case, it is somewhat similar to what we did the last time about the triangle, equilateral triangle. And in that we removed the central equilateral triangle first and then from the sidewise. Similarly, here also we are going to do the same process, but in this case we are going to remove from a square, and for that we can just draw an approximate figure. So we are given that we have a square and whose side is given as A, and it says that we are going to remove the central square will be moved first, and therefore we can just divide this entire square into so this is a central square and which is to be removed first. So it means we have given the side A, and so this is going to give us a 3x3 grid, and this 3x3 grid, if you remove the central one, so this 3x3 grid is going to give us 9 equal small square, and if we remove the central one, so we can say remove the central square, and this will be leading us to that we have only 8 remaining small squares. So we are left with only 8 remaining small squares. Okay. So it means that this 8 remaining small square, it is going to have a side of a/3. Therefore, from here we can say each side will be equal to our a/3. Okay, so this is our first iteration. And similarly, in the second iteration also, we have remaining 8 squares, and we are going to divide that into 3x3 and remove the central square, and this is going to this process will be continuous. Okay. So this was our first iteration. or we can say first step also. This is your first iteration, or we can say this is your first step in which we remove the central one. Now we are left with these 8 squares, 1, 2, 3, 4, 5, 6, 7 and 8. So we can pick, suppose we pick this, the first one, and here also in the second iteration, once again we are going to divide it into, and here also we are going to remove this, the central one. And once again this will be our 3 by 3 grid, and 3 by 3 grid, so obviously there will be total 9 squares, and if we remove 1 we are left with 8. Okay, so we are left with 8 small square per parent square. Okay, so we can call this as parent square 1, parent square 2, parent square 3, parent square 4, parent square 5, 6, 7 and 8. So this is our parent square number 1, and parent number square 1 will be, we are going to get this as 8 small squares per parent square. Per parent square. So it means the total number of squares after the second iteration, or we can say second removal. So from here we can say that total number of squares after second removal, and that will be 8 from the first iteration multiplied by per square, which will be giving us total 64 squares will be there in the second iteration. And here we are supposed to find out the moment of inertia about the axis which is going to pass through the center of the original square. And therefore here we can just say that we are going to have total 4 squares that will be our corner squares, and that will be a total 4 squares that will be our edge squares. So parent number 1, 3, 5 and our 7, they will be, we can call this as our corner squares, and this our P2, P4, P6 and P8 we can call them as our edge square. Therefore we can write, so let me draw it here again. So we are supposed to find out moment of inertia of the axis which is passing from the original square, and we have this as parent number 1, 2, 3, 4, 5, 6, 7 and 8. And after this we are going to have our 4, these are our corner square, P1, P3, P5 and P7 will be corner square, and 2, 4, 6 and 8 we can call them as our edge square. And so based on this we can find out what will be the side length of each square as well as the area of our per square. Okay, that we can easily find out. So we can say that our stage is suppose 0, nothing, no square is removed, so we can call this as a stage, and number of squares and we have our side length, and then we have our area per square. Area per square. So we start with our stage is 0. We have only one square, complete square. Okay. So obviously its side will be our A and its area will be equal to our A square. Now we come to our stage 2. Stage 2 is nothing but, stage 1. Stage 1 is nothing but our iteration 1. In iteration 1, the number of, we have already removed this middle square. So therefore the number of squares will be 8. And the side length will be coming now as our L by 3. And the area per square will be coming as our L square by 9. Similarly, we come to stage 2 and number of squares will be now 64 and the side length will be coming as our L by 9 and the area will be coming as our L square by 81, and this will be a continuous process. Therefore we can say if stage our K, and so this 64 can be written as 8 raised to power 2 and this 8 can be written as 8 raised to power 1. So if stage is K, so our side will be, number of squares will be coming as 8 raised to power K, and our, this can be also written as L 3 raised to power 1. This can be written L 3 raised to power 2. Therefore we get this as L and 3 raised to power K, and our area we can write this as our L square divided by 9 raised to power K. So if there are a number of K stages, so we got that number of squares will be 8 raised to power K, side length will be coming as L 3 raised to power K, as well as the area, that is L square 9 raised to power K. And so therefore we can say that at each stage, if we are removing the central square, so which will be our the side will be 1/3 of the our parent square that we have already calculated, and remaining are our only these 8 squares. So let us find out what will be the respective their moment of inertia as well as our this the mass, how it will be distributed. Okay. So once again we start with step number 1, or we can say the stage 1. Okay. And so let us assume that the stage 1, the contribution in the moment of inertia is our I1. And for stage 1, we know that we are having the squares, or we can say number of squares are our 8, and our side is our A by 3. Okay. And mass, suppose it is given as M1, so M1 will be equal to total mass divided by 8. Okay. So this will be our for one small square. Therefore we can say that for one small square, we can find out its center of mass, moment of inertia with respect to center of mass, that we know is our 1 by 6, and its mass and the square of the length, that is our A by 3 and whole square. Okay. And M1 is our M by 8. So therefore we can write this will be coming as M A square, and this is our 432. And we are having total 8 squares. So we can find out the total moment of inertia of all the squares. Therefore we can say that total moment of inertia of 8 squares, and this 8 square is only with respect to their center of mass, and this will be coming as 8 times ma square divided by 432, which gives us our ma square, and become this as our 54. Now we have to remember that we are calculating the moment of inertia. We have to calculate rather the moment of inertia with respect to the axis which is passing through the center of the bigger square, the original square, and we found out the moment of inertia of the individual squares. Okay. So we found out the moment of inertia of this individual square with respect to the center, respectively the second one, third one, fourth, fifth, sixth, seventh, and eighth. So we know the moment of inertia. This will be I1, I2, I3, I4, I5, I6, I7, and I8. Okay, which we have called as this as ICM. Okay, so we found out our this moment of inertia. One second, let me call this as ICM. So this is our ICM, not I1, I2. So this is our ICM 1, we have our ICM 2, ICM 3, and this is our ICM 4, ICM 5, ICM 6, and ICM 7, and we have ICM 8. So we got the moment of inertia for one small square, that is our ICM, and for total we got this as ma square divided by 54. Okay. And in this case we have to remember that we are supposed to find the moment of inertia of all these square with respect to the center of mass. And in this case, we are having 4 squares that will be our corner squares, and 4 squares which are our edge squares. So the distance for this all the squares will be different. Okay. So we have our, you can say, 4 corner square as well as 4 edge square. So we are going to find out, we are rather going to use parallel axis theorem to find out the moment of inertia of their respective small squares at the center. Therefore we can say that parallel axis theorem, and so we can write that we have 4 corners, and these 4 corners are our P1, and we have this as parent 3, parent 3, and we have this as parent 5, and we have our parent 7. Okay, so these are the 4 corner square, and we can call this distance as DC. So this distance will be our DC. So we can easily find out the distance DC. So we can say the 4 corner squares, we can say our DC square will be equal to twice a by 3 and whole square, which gives us, this will be our 2a square upon 9. And so we can find out that the contribution because of these 4 corner squares towards the moment of inertia. Okay. So we can write this as our the moment of inertia of 4 corners square, and let us call this as center as O. Okay. So we can say at O. So that will be our 4 times and the mass of individual and the distance square, that is 2a square upon 9. Okay. So this will be coming as 1 by 9 and ma square. Okay. And similarly we are having 4 edge squares. So you can say we have 4 edges, and 4 edges we are going to get their distance square will be equal to our a by 3 whole square, giving us a square by 9. And similarly, their contribution towards the moment of inertia at the will be coming as about 4 times m by 8 multiplied by a square by 9, and which comes as 1 by 18 ma square. And therefore we can write that their total combination, so we can say we can for our one second ma square by 54. Okay, so here let me correct myself. So this is the moment of inertia of the 4 corner squares. Okay, later on we are going to use the parallel axis theorem to find out the center. Therefore we can say that the moment of inertia, because of our these total 8 squares, so you can say for stage 1 we said that moment of inertia at our center, which is our I1, will be equal to our ICM, that was the total moment of inertia, which is ma square upon 54, and plus, and that will be equal to 1 by 9 plus 1 by 18. So this will be coming as our 1 by 9 plus 1 by 18 ma square, and this comes as our 5 upon 27 ma square. So this is the moment of inertia for our stage 1. And now, so everything will be now repetitive. Repetitive means like we resolved our bigger square into this 8 3 by 3 grid. Similarly, we are going to take one parent square and once again resolve it into 3 by 3. Okay, similarly take the second parent square and resolve into 3 by 3. So this process is continuous. Okay, so that will be a recursive process. Okay. Therefore, we are going to devise a scaling factor, because the next square modification will be the copy of the original modification. Only difference will be that the size is going to reduced. So because of that, we are going to find out the scaling factor. So let us first of all define once again whatever our previous condition. We know that our original square side was our A, and we found out that from stage 1 we computed that stage 1 moment of inertia, which is our I1, we found it as 5 upon 27 and ma square, and this moment of inertia is at the center O. Okay, so we found out because of all these 3 by 3, or we can say 8, and at the center, okay, which we found out as I1, and that is a 5 upon 27 ma square. Therefore, we can say that our each later stage is made of 8 copies okay, because from every stage we are going to remove one square. So total will be our 3 by 3 grid. So if we remove one square, we are left with only 8 squares. So it means there will be 8 copies of previous stage pattern. Of previous stage pattern, okay, and placed inside eight parent squares. Therefore, we can say that the linear scale factor from one stage to next will be equal to 1 by 3. Therefore, we can say that our linear scale factor from one stage to next let us suppose that is given as, which will be equal to our 1 by 3. Okay. And we know the general formula for our moment of inertia, and with respect to the scaling, if the shape is fixed. So every time we divide, we are always going to divide a square. So the basic shape of the object will be always fixed. It will be a square. It will be of larger area as well as a smaller area, but the basic shape is going to remain same. So we can say for the fixed shape, our moment of inertia scales as I is proportional to our mass multiplied by the length square. Okay. So this is the scaling of our moment of inertia. So let's find out how this is going to work with respect to stage 1. Then we can replicate it to as many stages we wish to. So we start with our single copy scaling. So we assumed that we are having a total mass is our capital M, and we also wrote that there is a linear scaling, that is our A by 3. Okay. So we can say that we have a linear size, and that linear size is suppose capital L, and for stage 1 this capital L will be equal to our A by 3, and we call that its moment of inertia for the first stage is our I1. Therefore, we can write that I1 will be proportional to our mass and its length and square. Okay. So if we use some kind of constant, that is our C, it doesn't matter. So we can say our I1 will be equal to constant C, and we have this as mass and our L square, that's our length square. Okay. And like we said, that for the next stage, that is stage 2, there will be geometrical similarity to this first stage. Okay. And here I forgot to mention that this is stage 1. This is our stage 1. Okay. So from stage 1, let us consider one of the 8 copies. So we can say considering one of 8 copies, and one of the 8 copies that appears in next stage, which is nothing but a stage 2. And for stage 2, we can say that copy it is going to have geometrical similar to our first stage. We are going to have geometrically similar to first stage. But with linear scale, which is our S, will be equal to 1 by 3, okay, relative to first stage. And its mass, so you can say our mass of the copy will be equal to total mass and into the 8 equivalent objects, okay. And therefore we can say that moment of inertia of 8 single copies, or we can say moment of inertia of a single copy, which will be equal to over I copy, and I copy we can write this as our, using the general formula, which is our C multiplied by M L square. So this comes as I copy will equal to C mass of the copy, and we have the scaled version of the length and its whole square. And therefore we can just substitute the formulas. So we get this as I of copy will be equal to C M by 8, and this comes as our S square and our L square. Now we have our 8 copies, so therefore we can say for stage 2, so we have stage 2 and its moment of inertia will be equal to I stage. For the second one will be equal to 8 times the moment of inertia of a single. So we get this as 8C M by 8, and we have S square and our L square, and this 8 and 8 cancels out, so we get our I stage for the second one will be equal to, and we have this as CM L square, and we have our S square. But we know that this CML square is nothing but our I1. Okay, so this is nothing but our I1. So we can say that the moment of inertia of the second stage will be equal to S square times our I1. Okay. So this was the second stage. Similarly, we can replicate it for our kth stage. Therefore, we can say that for kth stage, we can write that our moment of inertia of the kth stage will be equal to our I1, and this comes as S 2 raised to power k minus 1. Okay, and we can substitute value of S. S is our 1 by 3, so that will be coming as I1, and this is 1 by 3, and this is 2 times k minus 1. Therefore, we get that for the kth stage, we are going to get this as a I1 1 by 9 and k minus 1. Okay. So it means from here we can just write the sequence, and the sequence will be I1 times 1 by 9, I1 times 1 by 9 square, and so on. Okay. So it will be a continuous process. Therefore, from here we can say we are going to get this as I1 and we have I1 upon 1 by 9, I1 multiplied by 1 by 9, and we have this as I1 times 9 square and so on. Therefore, this is nothing but a geometric series, and we know that moment of inertia we can write in the form of a geometric series. So we can say sum of geometric series, sum of geometric series. Therefore, we can write that our moment of inertia I will be equal to our summation, and this comes from 0 to infinity, and we have a I1 and 1 by 9 raised to power n, and we can just write this as I1 and 1 upon 1 minus 1 by 9. So this gives us I1 times 9 by 8, and we know that our I1 is 5 upon 27 ma square. So we can say that our I is equal to 5 upon 27 ma square, and we are multiplying it by 9 by 8. So this comes as 5 upon 24 ma square. So it means this is our moment of inertia of the series. And the only major difference here is that we have to consider that there will be two different distances. Distance toward the edge will be different, and distance toward the corner will be different. Okay. So we come to the next question. And it states that a particle move in a circular orbit under the influence of central force that varies inversely to as the cube of the distance, that is f upon 1 upon r cube. Show that the particles can also move with a uniform radial velocity vr, either inward or outward, while still remaining under the action of this force. This situation represents a case of neutral stability, causes the particle to move radially at a constant rate. Find the relationship between the angular coordination theta and the radial distance r for the motion with a constant radial velocity vr. So in this case, we are talking about an object which is moving in a circular path, and it is given the relationship between the force and the radial distance r is given in the question. So we are going to use that particular relationship to find out its the relation between our theta, and that was asked for. So we have to here remember that the distance between, the relationship, it basically a inverse cubic relationship. That is the important part here. And okay, so we are going to start from there only, and let us say that we assume that the particle is having a mass of our mu. So let us find out the motion in our polar coordinates, and that is going to help us to find out our theta. So we can say motion in polar coordinates and for that we assume that we are having a particle of mass mu and moves in a plane under a central force. Moves in a plane under central force. And we can write that formula as our F will be equal to our F of R, and we are having for directional we can use our R unit vector. Okay. And this is central force, therefore we can say that there will be no torque, and if there is no torque, or we can say there is no external force, we can also say that our angular momentum is conserved. Angular momentum is conserved. And let us resolve this into radial as well as tangential direction with respect to our theta. So we can say that our resolving acceleration in radial and tangential direction so first is our radial component. For radial we can write our mass, and we have a double derivative of our this radial distance minus our r double derivative of our theta, and that will be equal to our F of R, because the force is only in the radial direction. Okay. And this secondary term, which is this term, this is nothing but representation of our centripetal force, or we can say centripetal term. So this is our centripetal term. Now we come to our tangential direction. And for tangential, we can write this as a mu, and we have our r double derivative of theta plus twice r theta, and will be equal to 0. Okay. And from here we can also write that its derivative with respect to time, and we can generalize this as our r square theta single derivative is equal to 0. And we know that our angular momentum is conserved, so we can say that angular momentum is conserved, therefore we can say that our L will be equal to our mu r square, and this is theta naught first derivative, which is nothing but our constant. From here we can write that our theta first derivative will be equal to L upon mu r square. And now we can express the relationship in terms of our tangential velocity. So we can say that our tangential speed we have a tangential speed, and suppose that is our v theta, and this v theta will be equal to r times single derivative of our theta, and we can substitute it. So from here we can say that our v of theta will be equal to r times theta naught theta single derivative we know is our L upon mu square, so this comes as L upon mu r square, and this r square cancel with this r, so we get this as our L upon mu times r, and if we square both sides we get this as theta v of theta square is equal to L square upon mu square and R square. So now we can find out about, we are going to find out the total kinetic energy, and the total kinetic energy once again is going to have two components, okay, radial as well as the tangential. So let's find out the total kinetic energy, and we can say that the velocity has two components, total velocity rather. You can say total velocity has two components, and we can write that form as our v square is equal to the radial component and our tangential component. So respectively we can write it form of our r single dot square plus, and theta we just found out is our L square upon mu square and our R square. Therefore we can say that this total kinetic energy, if represented as T, so we can say that our T is equal to our half m v square. We just found out, so we can write this as our half mu, and we have this as R single dot square plus half mu, and this comes as our L square upon mu square R square. Okay. And so we can just cancel out this mu, so we are going to get this as our half mu R dot square plus L square upon 2 mu R square. Therefore the total energy let us suppose our E will be equal to the total kinetic energy, that is T, and the energy with respect to our radial distance R. Okay. And we can say that this is equal to 1 by 2 mu R dot square plus L square upon 2 mu R square plus V of R. And we can combine this term and call this as our V effective, that is dependent upon our R. So we can say that our V effective R will be equal to our V of R plus L square upon 2 mu R square. And now we are given that a particle is moving in terms of the inverse cubical law, that's a force. So therefore we can say that our F is equal to minus k upon r cube. Therefore from here we can use this force to find out the energy at a distance r, which is a simple derivative. Therefore we can say that a force will be equal to minus dV upon dr. So we get this as a dV upon dr is equal to minus of F, which will be giving us k upon r cube. And if we integrate both sides, we get this as our V of r will be equal to integration k upon r cube and d of r, which will be coming as minus k upon 2r square plus c. And if we assume that for infinite distance, radial distance at r is infinity, so there's energy will be equal to 0, or we can say that v of infinity is 0, which gives us that c will be also equal to 0. Therefore we get that our v of r will be equal to minus k upon 2r square. And like we said that our angular momentum is conserved, therefore we can say that angular momentum is conserved and all the forces are of a central. Therefore we can say our L is equal to mu r v of theta, and we can substitute our v theta, that is why L is equal to mu of r will be equal to r theta first derivative, which will be giving us mu r square and theta derivative. Okay. And we also calculated this, so let me write straightforward. Theta first derivative is equal to L upon mu r square. So we can say that our total kinetic energy I think we calculated this also. T we already calculated, so let me substitute it and get our total kinetic energy. So we can say that our total energy, which is our E, is our 1 upon 2 mu r dot square plus L upon mu r square, and we just calculated our V effective, that is minus k upon 2r square. This is minus k upon 2r square. And from here we can also find out our V effective. V effective upon r, this gives us our V of r plus L square and 2 mu r square. We substitute our V of r, which is a minus k 2r square plus L square upon 2 mu r square. Therefore we get that our V effective r will be equal to 1 upon 2r square L square upon mu minus of k. And for our circular orbit, we know that the derivative of our radial distance will be equal to 0, and its double derivative will be also equal to 0. So we are going to use the condition for circular orbit. Condition for circular orbit, and we can write that condition that its first derivative will be equal to 0, as well as the second derivative will be also equal to 0. Therefore we can write the equation for our radial force equation. You can say we are having radial force equation, which we have already written, is our mu is our r double derivative minus r theta square is equal to our f, and f we know is our minus k upon r cube. And like we said that our for circular orbit the double derivative is equal to 0, so we substitute it and we get that our for circular orbit we have that our r double derivative is equal to 0, so we get this as our minus of mu r theta square is equal to minus k upon r cube. And from here we get that theta single derivative is equal to k upon mu, and 1 upon this comes as our square, and it is our r square. Okay. And we know that our that L, that is our angular momentum, our L is equal to mu r square theta single derivative, and we substitute it, we get the angular momentum L will be equal to our mu r square 1 upon r square multiplied by square root of k upon mu, and this square and square cancel out, so we take mu inside the square root, so this comes as square root of q times mu, or we can say that our L square is equal to k times mu. Okay. And so find out what will be our effective potential at L square is equal to mu k. So we can say the effective potential at L square is equal to mu k, and that will be giving us our L square upon 2 mu r square. We substitute value of L square, which is our k times mu, will be equal to 2 mu square, and here this mu and mu cancel out, this comes as our k upon 2r square. Therefore our effective potential at distance r is equal to minus k upon 2r square and plus k upon 2r square, which comes as 0. So it means it is a constant and flat for all values of r. So it means effective potential is basically independent of r. So we can say this is constant and flat for all values of our r. Now we can use our radial energy equation. Radial energy equation, and that is our E is equal to half mu r single dot square plus V effective at a distance of r. And like we said, our V effective is equal to 0. Therefore from here we get our radial energy E is equal to over half mu r dot square, and from here we can say that our r dot is equal to plus minus square root of 2e divided by mu, and which is nothing but single dot derivative of is our velocity. Therefore we can say that our v is equal to, if we take value greater than 0, so this will be square root of, where this v is greater than equal to 0, and therefore we can say that our single dot v will be nothing but our outward, and if our r single dot is our minus of v, then this is our inward, which were asked in the question itself. It means the radial velocity is uniform and it is only in the radial direction. So we can say that our radial velocity is uniform and in the radial direction. Okay. And finally we are going to find out our theta. That was our last step, last part in the question itself. Therefore we can say that we are going to find this theta that will be dependent upon our r for our radial velocity, which is given as our v. And we already know that our angular momentum A is equal to mu upon k and its square root, or we can say that our L square is equal to mu upon k, and we have already found out our theta first derivative is equal to L upon mu r square. We substitute value of our angular momentum, that is our L, which comes as square root of mu k divided by mu r square. Therefore, our theta first derivative will be equal to 1 upon r square, and this comes as our square root of k upon mu. Okay. And so this was our theta, and we can also find out our in terms of our, okay, let me write it another way also. Therefore, we can say that our